Hi, welcome to part two of this video where we model stresses in rotating rings using a 2D axisymmetric case in ANSYS FEA. Now, in the first video, I showed you how to set up the analysis and run it. So to recap, I set the geometry here to the 2D behavior to axisymmetric. We set our material properties, created our mesh. And then for our boundary conditions, we set the rotational velocity about the y-axis at the global origin, so 0, 0, 0. And then we also created a region of symmetry that is defined by the normal plane represented by the y normal vector, or in this case, the xz plane. And so now let's add some stress results and we'll compare them to hand calcs. So I've added here the normal stress. And if you want to add a stress, you left click solution, right click, insert. We'll do another normal stress here, normal. And we'll look at the z-axis stress, which in the axisymmetric case, the z-axis will represent our hoop stress, or the stress in the theta direction. And then if you want to look at that result, you can right click retrieve result if you've already uh, solved the analysis. So we'll cover some theory real quick, but the stresses in a rotating disk or ring, I pulled these equations out of Shigley's mechanical engineering design. And for these equations to apply, there's a few assumptions that need to be made. I actually have here a copy and paste error, sorry. So the outer radius has to be greater than 10 times the thickness. So for our geometry, our thickness was 1 inch, and our outer radius was 10 inches. So we meet this requirement. This is actually greater than or equal to. And so this is the equation that defines the hoop stress. In the case of ANSYS, this would be our z, our sigma z, or our tangential stress, or the stress in the theta direction. And then this is the equation for the radial stress. So it's a function of your density, the rotational velocity, Poisson's ratio, and the inner and outer radius. And likewise for the stress in the radial direction. So I've done the calc for our case. Our inner radius was 5 inches. Our outer radius is 10. Our rotational velocity was 500 radians a second, which is 4,775 RPM. Now, if you're working in English units, there's something called the slug. And for this calc to work out with inches, you need to use the slinch per inches cubed, which is a slug inch. And our Poisson's ratio is 0.3. And so we look here, the inner hoop stress is 15,953 per the hand calc. And we see here that the max value is 15,953 and the outer hoop stress is 6,995. And that agrees with our hand calc. And so I plotted here the hand calc versus the ANSYS results, and they agree, which we would expect. Now, one thing I should mention is that because the radial stress is positive, when ANSYS goes to calculate the max shear stress from the min and max principal stress, the axial stress is 0. So the max shear stress is really, in this case, a function of the hoop stress just divided by 2. And you can see here if I plot the maximum principal stress, we see that it aligns with the hoop stress. And our axial stress is very close to 0. So I plot normal stress in the y direction. You'll see that it's very low compared to the hoop stress, almost 0. Now, one thing I'll show you is if you want to post-process nodal results, I've previously shown that you can do it by mapping stress to a path. Now, the other option is to select an edge, and we'll plot our stress on that edge. So let's say we'll look at hoop stress, so the z-axis, and we'll right-click retrieve that result. Now you can actually export these results. If you right-click on your stress that you want to export, you can go here to export as a text file, and we can call this the hoop stress, and then you can save that file. Now, if you want to look at the files uh, associated with your analysis, you can right-click on Solution and click Open Solver Files directory. And you'll see here the ANSYS files associated with your analysis. So if I go back to my main folder, I can click on the text here and open it up, and you can view the stress results for that particular post-process result. And it'll have nodal number and your XY location, Z location, and then the stress that you decided to export. Now you can also do this, you can also include all of the stresses in the stress tensor. So if you want all the tensor components, you can right-click Insert Stress, Vector Principal, and then right-click Retrieve this result. And this graphically, it will show you the principal stress vectors. But you can right-click on this and hit Export, Export to text file. But before you do that, you'll want to make sure that your export options are set to show tensor components, yes. So if you go again, if you right click on here and export to text file, we can call this maybe tensor. And then if we open up that text file, you'll see that you'll get the XY, you'll get the tensor components in the coordinate system that your vector principal is set, and that should be the global coordinate system. So we'll see here, we get all 6 components of the 3D stress tensor. And yeah, that wraps up the second part of this video. Thanks for watching, guys, and looking forward to making more videos for you.